All right, let's start today recalling a fundamental theorem from our past, because we're going to talk about the fundamental theorem of line integrals. And previously we looked at a fundamental, or part of the fundamental theorem of calculus, and that was the integral from a to b f prime of x dx equals then f big F at a. So yeah, if we've got this derivative that we can integrate, then we get back to the antiderivative, so to speak. Gives us a way to evaluate a definite integral. Well, there's a version of this for line integrals. And here it is. Suppose C is a smooth curve the vector function RT from t going a to b, and also suppose f is a function whose gradient vector gradient of f all right, so C is this smooth curve defined by the vector function, and then f has a gradient vector that's continuous on f as well. Then here's the payoff then. The integral of C for our gradient vector dotted with differential dr. Turns out that's going to just be equal to f evaluated at r minus f evaluated at r of a. All right, so here's the significance of this. This is the fundamental theorem of line integrals. Very similar to the fundamental theorem of calculus, because what we've got here, r of b, that's our terminal point for our function, right? Because we're going from a to b for this curve r of t. So r of b, that would be the terminal point, and r of a would be the initial point. And so what this says is this line integral then is f evaluated at the terminal point minus f evaluated at the initial point. So yeah, this line integral is okay, so that's it. Okay. So much like the fundamental theorem of calculus, yeah, this line integral really is just depends. You just have to calculate the function value at the terminal point minus. So it just depends on the function value at those two values. And one other thing we might note here is that since we've got the gradient of f, and we can find this function f, this is a conservative vector field too. So if it's a conservative vector field, basically what this is saying is you just have to evaluate the integral, you just have to know those two function values for f. Okay? And so, for example, let's evaluate. Probably need more room here, so. The line integral, gradient of f dot dr, where it works 2 dimensions, 3 dimensions, 4 dimensions, how many ever you got. Cosine pi x plus sine pi y minus xyz. The function in C is any path from 1/1/2 to Okay. So previously on our line integrals, we specified our path, but really it doesn't matter here, because since we know the function by the fundamental theorem of calculus, theorem of line integrals, we know that this is just the function value at the initial point minus the function value at the terminal point. And so R of t can be any path that goes from R1, 2 to 2, 1, -1. And okay. All right. So our integral from C gradient of f dot dr is function value evaluated at R of A. Well, R at A, that's our initial point, and so that would be 1/1/2. I'm sorry, it's R of B minus R of A, so this would be our R of B. This is our R of A. So f of R of B, so it'd be 2, 1, -1, minus f of 1, 2. And so to evaluate this line integral, all we have to do is plug those into our original function. So 2 for x, 1 for y, -1 for z, so that would be cosine of 2 pi plus sine of pi times 1 plus pi minus x times y times z, so that would be 2, -2, so minus would be +2. Minus 2, f valued at 1/1/2, 2, so that would be cosine of pi plus sine of pi over 2, because the y is a half, and then minus 1 times a half times 2, that would be just be 1. This is either cosine of 2 pi is 1, sine of pi is 0, and cosine of pi is 31, sine of pi over 2 is 1. We got 3 plus 1. All right, so it's 4. Okay? All right, so yeah, it turns out really no integrating to be done because of this fundamental theorem of the line integrals, the way it turns out. And the path doesn't matter either, which is not the case for a lot of our integrals. A lot of, of the line integrals. The first ones, the first line integrals that we worked was definitely, if we changed the path, that changed the value of the line integral. Well, in the case of conservative vector fields, that is not the case. It's independent of the path. And so let me go through a couple of just definitions here. Let's say we've got F is a conservative vector field. I'll continue because I want to review. All right, number 1. We talked about it already today previously, but just a reminder, F is conservative. How? How is F conservative? If there is a function F such that the gradient of F equals vector field F. Okay? Yeah, so if there's F is a conservative vector field, if we can find, or if there is a function such that the gradient of F, the vector field formed with the partial derivatives, and that equals our big F vector field. And recall that if that's the case, F is called the potential function. Okay. So that's what we mean by conservative. Okay? All right. Then a line integral of vector field F dotted with dr, that is said into the path line integral F dot dr over C1 equals integral line integral F dot dr 2. So this line integral is independent of path if that's equal for any path C1, C2 with the same initial and terminal path. Makes sense because, yeah, if you've got any two paths and the line integral is the same no matter what, makes sense to call that independent of path. So, from our previous theorem, then, we've got the gradient of f dot dr. That's independent of path because we said it didn't matter what the c was as long as you knew the initial point and the terminal point. You can calculate this integral, so it won't matter the path. So this is independent of path. Also note there that since by number 1 here, if we've got f being conservative, then we've got the gradient of f equals our vector f, and so if f is conservative, then our line integral f dr, we can rewrite it as the line integral gradient of f dot dr, and so we know that's independent of path. So if f is conservative, then it is independent of path. Line integral dot dr is independent. In other words, we can evaluate its line integral over curve C by just doing the potential function's value at the initial point and the terminal point, subtracting those two. Okay? All right, now, just a couple of other definitions of words you might see pop up. Probably seen these before. Just a reminder. Path C is closed if its initial and terminal points are the same. So yeah, you've got start here and then go around wherever you want to go. But as long as you wind up where you started, that's called closed. If you start somewhere and then finish somewhere else, that's not closed. Okay? Path C is simple if it doesn't cross itself. Cross itself, it's called simple. And so both of these would be simple. A figure 8 would be closed, but it would not be simple because it crosses itself. So anything where it crosses itself would not be simple. So simple, you just can't cross over. And then as far as region D here, region D is open if it doesn't contain any of its boundaries. Leave out the boundary points. It's called open for a region. And then region D is connected 2 points in the region. With a path completely in D. And so if we're talking about an area here, so that's region D, that's of course, that would be connected. If we have region D, it can have a hole in it, okay, so let's say that's region D. Now we can connect any, like a donut, we can connect any point in there to any other point, but, if region D happens to be, two separate entities, you can't draw a path connected to, from this point over here to another point from that one. And so that one would not be not connected there. That one would not be connected. And then region D is simply connected if it's connected, obviously, and there's no hole. So my second one here, so this one would be simply connected also, but this one is connected, but it's not simply connected because it has a hole in it. Okay. All right. One other fact here before I move on. If integral FDR, the line integral over C, is independent of path, then line integral C FDR equals 0 for every closed path. Makes sense because if it's an independent path, then we can say it's conservative, and then our conservative vector field, we just have to do the potential function, evaluate the terminal point minus the potential point at the initial point. Well, if it's a closed path, the initial point and the terminal point are the same. Those subtract out. Therefore, it would be 0. So, and this also works vice versa. So, all right. Now, all well and good, but what we need to look at here next then is if we need to know, is there a way to determine if it's conservative? Because if it's conservative, then the path doesn't matter. It's path independent, and so we can evaluate the line integral pretty easily. If it's not conservative, then that's a different matter. But if it is conservative, then we have a nice way of evaluating the line integral. So is there a way to determine if a vector field is conservative? We haven't looked at that yet. Well, it turns out, yes. Turns out there's a theorem. Let F equal, we're going to call it Pi and Qj. For our component, P and Q are going to be our component parts. So let that be the vector field. On an open and simply connected region D. Then if has continuous first order partial derivatives that's true, then F is conservative. Okay, so it turns out, and they go through the proof in the book. Like a time, I'll let you look at that, but it actually gets back to Clairaut's theorem, I think. But anyway, yeah, it turns out if the partial derivative of P with respect to Y equals the partial derivative of Q with respect to X, if those are equal, then it turns out the function, the vector field is it's called conservative, or is conservative. Which means, in other words, there's a potential function where the gradient of f equals the function, the vector field, big F. All right, so let's determine. A couple of these are conservative. A vector field xy equals not xy, x squared minus yx I plus y squared minus xy. Okay, and so we've got the p function is x squared minus yx, and q is y squared minus yx. And so for this to be conservative, we need the partial of p with respect to y. See if that's equal to the partial of q with respect to x. The partial of p with respect to y, so that would be 0 and minus x, so it'll be minus x. The partial of q with respect to x, what we want to do there, well, that's 0, that would be minus y, not equal. And so that determines no need to look for potential function for it, where the partial, the gradient equals f. Okay? And its line integral would be a little more difficult to evaluate. All right? Here's the second one. The vector big F equals 2x e to the xy plus x squared y plus x cubed e to the xy plus 2y the general point. So this is our P, this is our Q. And so what do we need? The partial of P with respect to Y. Well, that's this part. First of all, that would be partial with respect to Y. It would just be 2x. And we're just doing the xy derivative. So e to the xy derivative would be e to the xy. And that's what we're doing it with respect to Y. You need to do the derivative of the power, so that would just be x. Derivative of that with respect to y, well, we've got 2y, so we've got to do a product rule, x squared y times the derivative of e to the xy, e to the xy times derivative of power, which would be x, right? Plus, then flip it, e to the xy times the derivative of x squared y with respect to y squared. So if we clean that up, this is 2x squared e to the xy, and that's 1x squared, so we've got 3x squared e to the xy plus x squared y e to the xy. That's our partial of P with respect to y. So look at the partial of Q, but with respect to x. So Q is that, so that would be you're doing with respect to x, so, we've got a product rule, so that would be 3x squared e to the xy, plus then reverse it, x cubed times the derivative of e to the xy, which would be e to the xy times y, doing with respect to x, plus then, 2y with respect to x, that's derivative 0. And so, look at that. 3x squared e to the xy. Oh, yeah, this one is x cubed. Sorry. Yeah, we got x squared times x there, so it's x cubed y e to the xy. So those two are equal. Exactly the same. So, that tells me what is conservative vector field. All right. Now the question is, well, if we have a conservative vector field and we know it's easy to evaluate a field, the line integral for that conservative vector field, because all you have to do is the potential function initial point minus potential function at the potential function at the terminal point minus, so here it is, if f is conservative, then our line integral over C, doesn't matter the path either, that's going to equal the potential function at your initial value minus potential function at the terminal value. Oh, the other way around. Keep getting those backwards. Okay, so anyway. We can do that. So if we could find the potential function for big F, then we're in pretty good shape for finding a line integral if we want to do that. Okay. So how can we find the potential function for well, it turns out let's think about it. All right, so if f is conservative, then we know f of xy exists such that the gradient of f equals df, right? Well, we've been noting for 2 dimensions f, we're calling it pi plus qj. All right, then our gradient of f equals the partial, one way we could write it, the way they write it, about 2 dimensional, then the partial would be, the gradient of f would be the partial of x with respect to x, partial of f with respect to y, be the j component there. And so, we can put 2 and 2 together here. If that's the case, we know these two are equal, then wouldn't it say that the partial of f with respect to x must equal p, and then the partial of f with respect to y must equal our q. All right, well, this gives us a start here, because now, think about it, if I integrate with respect to the appropriate variable, integrate this, of course this is the partial with respect to x, so if I integrate this, I get the function f of xy, right, because it's antiderivative, so we're going backwards, and so with respect to x, of course, and so wouldn't that equal the integral of p dx? I do believe so. And also then, if we integrate the same way, but this one with respect to y, that'll just give us f of xy equals the integral of q dy. Okay? So we wind up with 2 possibilities here for finding our f of xy. That's our goal here. We know it exists, and so f of xy, and sometimes you use one, and sometimes you use the other. It just depends on maybe how easy things look. Okay. So yeah, these are, well, start with these, and then go to these, depending on which one we need, basically. Okay? All right. So this one then. Determine if f is conservative. Find potential function. Yeah. Okay, here it is. All right, so we've got f equal 2x cubed y to the 4th plus x, that's our I, plus 2x to the 4th. All right, so P is this, P is that. All right, so we don't know if this one's conservative, so let's see about it. Okay, so we're asking, is this conservative or not? So if it is, our partial of p with respect to y equals the partial of q with respect to x. That's our first thing we need to look at. So what's the partial of p with respect to y? Partial of p with respect to y would be 8x cubed y cubed. That's just x, so it's 0. The partial of q with respect to x, that would be 8x to the 3rd, y to the 3rd, and with respect to x, that's 0. Sure enough, those are equal, so it is conservative. So it is conservative. So since it's conservative, we would need partial of f equal to q and or partial of f with respect to y equal to q by the previous thing we spoke of, okay? All right, this would say the partial of f that'd be 2x cubed y to the fourth plus x. And this would say the partial of f with respect to y equals q, so that equals 2x to the fourth y cubed plus y. All right, so to find f then, that's what we're doing here, we can use either one. Because now if we integrate this with respect to x, we get f of x y equals the integral of 2x cubed y to the fourth plus x dx. And we can do the same thing over here, integrate but with respect to y, so that would be f of xy equals the integral of 2x to the fourth y cubed plus y dy. Neither one of them looked easier than the other one, so let's just do this one. Start with this one. Sometimes one might be easier than the other. Okay? All right. So that would say f of xy equals, so we're doing the antiderivative here, with respect to x, so that would be x to the fourth, so I divide by 4, so that would be 1/2 x to the fourth, y to the fourth, plus then x, antiderivative of that, 1/2 x squared, plus, since this is not a definite integral we're doing here, we've got to think about that extra part, the constant part of this. Well, if you think about it, we had that the partial derivative of f with respect to x, that's where we got this function. Well, the thing about it is the other part to this really could have been anything function of y wise, right? It could have been just about anything as a function of y, as long as it didn't have an x component, right? So, in other words, our constant part is some, call it h or g, we'll call it g, some function of y. Because, like I said, we came back, this is coming from the partial with respect to x. And so if we take the derivative of this with respect to x, yeah, that's going to give us this, because this is just some function of y. So it's a little bit of a twist, because yeah, we're dealing with partials here. F is some function of x and y. Anyway, okay? So the constant term is just, we can't say it's a constant necessarily. It might be just a constant, but it could be some function of y because of where we got this. All right. Anyway, all right. So we've got a pretty good rendition here. However, how are we going to determine this? We need to determine that a little better than just saying, well, it's some function of y. We need to know a little better. Well, we can do this really by, since this comes from the partial with respect to x, let's think about this. Let's do the partial now of this with respect to y. That'll help us determine this a little bit because, well, let's just look at it. All right. So let's do the partial of this with respect to y. would be 0. And then the partial of that with respect to y, that would just be whatever its derivative is. Okay? So you're asking, well, how does that help us? This is 2. 2x to the fourth y cubed plus g prime y. That's what we also know that the partial of f with respect to y needs to equal q. And so if we set that equal to the q here, we know that the partial f with respect to y also has to equal q. So we can see here that g prime of y, what does it need to equal? Well, since those two terms are the same, g prime of y needs to equal y. And so again, if we integrate this with respect to y, both sides, we get g of y, or by the antiderivative, g of y would just be the integral of y dy, and so that would be g of y equals 1/2 y squared plus, now we can say it's a constant since we're just dealing in a function of y there. So g of y turns out for this is 1/2 y squared plus c. So our f of xy, the complete f of xy function would be 1/2 x to the fourth y to the fourth plus 1/2 x squared plus, and now we know g of y is 1/2 y squared plus c. Okay. And of course, it's really easy to check to see if this is right for a potential function, because we know that the gradient of f must equal our function. Is that true? Well, our gradient of f is, it's just the partial derivatives are the components. So, all right, what do we got here? Partial of f with respect to x, so that'd be 4x cubed, so that'd be 2x cubed y to the fourth plus, this would be x, that'd be the f, partial of f with respect to x. Partial of f with respect to y would be also 2x cubed, x to the fourth y to the third. That's 0. That would be just y. Constant of 0. Hey, look at that. Components are the same. Ta-da. Okay.